Hello everyone, my name is Arpit Garg and I am one of the author of the paper Instance Dependent Noisy Label Learning via Graphical Modeling, and other authors are Cuong Nguyen, FELIX, and Gustavo Carneiro. We have divided our presentation into four main parts that are motivation, hypothesis development, methodology, and the research results. So initially, we have lot of unlabeled data. So when we provide the label to these data, there are three famous techniques that are crowdsourcing, specialist, and models. But due to the bad quality of the data or the different human perception or modeling or the human error, it's very easy that we can give the wrong labels to the instances. So these are the few real world examples in which it's very easy to provide the incorrect data. But when we provide the incorrect data and we provide the noisy labels to the machine learning would overfit after some time. So it would learn the wrong example. So we need a robust algorithm that can solve this issue. So before solving this issue, we need to find out which type of noise we want to consider. So basically there are three different type of noise that are symmetric noise, asymmetric noise, and instance dependent noise. In our case, we are more focused towards the instance dependent noise, which because it inclines towards the real world noise, as the noisy label is dependent upon both the instances and the clean labels. To solve this issue, we have adopted the graphical model from the mentioned paper. So in this graphical model, we have the instances X, noisy label Y hat, the image representation Z as the latent variable, and the clean label also as the latent variable. So if we follow the methodology and if we have X and Y hat, which are the instances and the observed label, we'll try to generate the latent variable Z and Y. For generating the latent variable Z, we'll use the set of encoders, and for generating the Y, we'll use the classifiers. And after generating these latent variable, we'll try back to reconstruct the X. So we'll use the decoder to reconstruct the instances. And after reconstructing the instances, we try to reconstruct the noisy label. As we try to reconstruct the noisy label, then this latent variable Y should give us the clean labels. But to solve the identifiability issue, we use the divide mix at that place. And for the reconstruction loss, instead of using mean square error, we use the continuous Bernoulli loss. The reason behind this is where if we use the mean square error, then we have to consider that the latent representation is a Gaussian distribution, and this is unbounded. So the Gaussian distribution is unbounded between negative infinity to infinity. And in the real world, we only use this weighted MSE, the highlighted part of weighted MSE, and we ignore all the other equation. Because of that, we need to reweight beta a lot. To solve this issue, we use the continuous Bernoulli algorithm. So in the continuous Bernoulli, we only need to learn one parameter, lambda, and we don't need to readjust other parameters. And to evaluate our noisy label algorithm, we tried our algorithm on various datasets, that's CIFAR 10, CIFAR 100, Animal 10, and Red Mini ImageNet. And we observed that at high noise rates, our algorithm gives better results, and it proved to be, and it also gave state-of-the-art results on various real-world datasets. Thank you for listening.